For 80 years, almost every computer on Earth has been built using a single shared blueprint. It's a design formalized by John von Neumann in the 1940s. The core rule is simple. The place where data lives, the memory, is kept strictly separate from where it is processed, the compute. Because of this, every calculation requires data to commute across a physical bridge to reach the processor. This architectural triumph defined the first 80 years of computing. But today, that same physical separation is the very thing slowing AI down. Modern generative AI models work sequentially, predicting text one token at a time. To produce a single word, a GPU must fetch gigabytes of model weights from memory and drag them across that narrow bus. This happens for every single token, over and over again. This chart shows the problem. Raw mathematical processing power has scaled exponentially, but memory transfer speeds have only grown linearly. Look at this gap. We've built incredibly fast processors, but they spend 70% of their time idling, waiting for data. We cannot solve this by just making the bus wider. Moving data across a chip creates heat and consumes massive amounts of energy. Physics provides a hard ceiling on how fast data can travel. Simply building faster von Neumann chips is no longer enough to meet AI's scaling demands. The tech industry is being forced into a total architectural departure. The leading alternative is a design known as spatial or data flow architecture. Instead of a centralized controller fetching and writing data in a loop, data flow chips distribute the work across the entire silicon surface. This diagram shows how hardware like Google's TPU actually mirrors the neural network it's running. The software nodes map directly onto the physical cores. Data cascades from one core to the next without ever returning to a central memory pool. This design turns computing from a series of stop-and-go fetches into a continuous heartbeat of data. This logic reaches its extreme with the Groq Language Processing Unit, or LPU. To maximize speed, Groq completely removed the off-chip high-bandwidth memory typically found in GPUs. In this schematic, you can see the results. Groq embeds ultra-fast SRAM directly on the die in a dense checkerboard pattern. This architecture provides 80 terabytes per second of bandwidth. Because data is stored next to the compute units, memory access is practically instantaneous. Groq also abandoned the unpredictable scheduling used by standard chips to guess where data should go. Instead, their software compiler pre-plans the movement of every piece of data down to the precise clock cycle. By removing the guesswork, the chip becomes a deterministic hardware conveyor belt, capable of generating hundreds of tokens per second. Does this shift toward data flow hardware mean the von Neumann design is finished? Not for everything. General-purpose tasks, like running an operating system or managing a database, still run best on traditional processors. But the dominance of a single universal architecture is breaking apart. Specialized data flow chips from Google, Groq, and Cerebras are taking over the heavy lifting in AI data centers. At the same time, compute-in-memory chips are emerging for edge devices, doing math directly inside the memory array to provide high performance at a fraction of a watt. Software engineers are also solving the bottleneck with new mathematics. Models like diffusion LLMs use parallel refinement to bypass memory limits without needing new hardware. The AI boom is forcing the first total rewrite of computer architecture in nearly a century. Von Neumann's blueprint defined our past, but the future belongs to machines that actually fit the math.